So today we're going to be going through linear models and we're going to go through how to construct them given a set of data. So as mentioned in the notes, linear models kind of just give us a visual way to see data and the different relationships between the data points and any flows or any sort of relationships happening between the data as well. So in this example, we'll go through an example later about linear models as well, but first we're just going to go through the basic linear equation, what each part of the linear equation is, and then we're going to go through a few examples just to see how it works as well. So linear models basically just assume that there's a linear relationship between the response and explanatory variable, so any differences that happened in the explanatory variable have kind of like a proportionate effect on the response variable as well. So one of the main concepts that the linear model works on is the line of best fit. So that's basically just a line that kind of goes through all the data points to find the best like straight line that can go through all the data points. Now in the example that we'll be going through later, we have a set of data that has like perfect points on the line of best fit, but that's not always the case. Sometimes data points will be kind of scattered nearby, but the line of best fit just tries to find like a straight line that goes through that data in the best way possible, so that it's going through like an average of all the data points basically. So you don't need to know the maths behind the line of best fit, or in some textbooks it might also be called the least squares method. You don't need to know all the maths behind it for apps, but we're just going to go through what it is, how it works, and how we can kind of plot it through a set of data as well. So in this example, we can see that the line of best fit, the equation for it is y equals mx plus c. Now, y is basically the response variable. So this is whatever you're trying to find, whatever the answer is. M is the gradient. So we'll go through that in more detail later, but it's basically kind of like the variance between the two data. So like the constant that is increasing or decreasing as data goes on. I'll explain it when we have like a graph to look at later. And then C is basically what is the y value when x equals 0. So in the next example, we'll go through all of this if it doesn't make sense yet, but that's the basic equation of the line of best fit or the least squares method as well. Now, let's look at an example so that we can kind of see how that works in real life. Let's say that you have a horrible plumbing incident at home and you have to get a plumber over. Now, there's a call out fee for the plumber. So that's when x is 0. I'll explain this in a second when we go through the graph as well. But there's a call out fee. So just for the plumber to come to your house, there's a fee that you have to pay him. And then for every hour that he works on the plumbing issue, there's extra money that you have to pay him. So this table basically just goes through what the costs are depending on how many hours he works and then how much money it costs you. This should also kind of remind you of the two-way frequency tables that we went through earlier as well. And then we'll just see how this applies to linear models as well. So here you can see that if he's worked 0 hours, which is basically just for him to just show up at your place, that costs you $40. So that's his call out fee. If he works for 1 hour, it costs you $100. So that means that his hourly rate on top of his call out fee is $60. So if you go through the rest of the table, you can see how like for each hour that he works, the cost that you have to pay him increases linearly as well. Now, if we were to plot this, we can see that at x equals 0, it's not at 0, so you still have to pay him some sort of money. That is 40, that is the call out fee. And then as you can see, it consistently goes up as the amount of hours that he has to work goes up as well. So again, as I said before, in this example, the dots just happen to perfectly sit on the line of best fit. That's not always the case. Sometimes you might just have random points here and there, but that would still be the best line for you to put through the plots regardless. All right, now let's say that you're trying to go through and find the equation, the y equals mx plus c equation for this particular example. Now we know what, so let's look at it again. C is the number when x equals 0. So here, when x equals 0, the number is 40. So we know that C is 40. Now, if we want to see what the gradient is, that's basically what number response variable increases by for each value of x that we go up by. So when we go to 1, the value is 100. So what's the difference between 40 and 100? 60. So the gradient is $60. Each hour that the plumber has to work, the cost that you have to pay him increases by $60 every time. So if we were to plot that, or if we were to come up with the equation for y equals mx plus c, we know m is 60 and c is 40. So the equation is y equals 60x plus 40. Now, you can check this if you go back as well. If we wanted to know, let's say we didn't know what the cost was if he worked at your house for 8 hours, we could say y equals 68 plus 40. So y equals 540 plus 40. 40, so we know it's $580. Now, wrong example, cut that out. Cut that out. Embarrassing, my brain isn't working. All right. I don't want to do this anymore. Okay. Oh, we go through an example later. Okay. Embarrassing. All right. Okay. How did I get this? Okay. Wait, is this wrong? Or is my maths wrong? What's 8 times 6? 48. Oh, wait, no. Never mind. I'm stupid. Okay. This is so annoying. I don't want to do this anymore. Okay. I was going so well. Okay. So another important part of linear modeling or linear equations is the coefficient of determination. Now, we don't have to know the details about the math behind this as well, but basically what it is r squared. Now, this value ranges from 0 to 1, and what it basically tells you is how much of the variance in the response variable is attributable to the variance in the explanatory variable. So let's say in this case, in a separate example that we're looking at, r squared is 0.8. So we know that the variance in the response variable, 80% of that can be explained by the variance in the explanatory variable. So in simpler terms, this basically just shows how much of the difference or the variance in one variable is caused by the other variable. So it kind of indicates the strength of the relationship between those two variables. Now, we obviously don't have to go into that much of the math behind this, but if you want more detail, then go back to our notes and we cover this in a little bit more detail. All right, so going back to the plumber example, another thing in relation to linear models that is important for us to know for apps is extrapolation. Now, extrapolation is basically we are given a set of data, and in that data, we don't have like every single value for the response variable that is ever possible, because that would be like an infinite amount. But sometimes we just need to know a certain value that isn't given in our table. So that is extrapolating data, given that we know what the y equals mx plus c equation is. So an example would be, let's say that you just had like a horrible plumbing accident and the plumber has to work at your house for 10 hours, which is a lot. Now, obviously, if we go up to the table before, we don't have a value for 10 hours. So we have to use the linear models equation that we came up with before to extrapolate the data and figure out how much it'll cost us if the plumber was to work at our house for 10 hours. In contrast, interpolation is basically when you just look at the table that you have and the data's already there. It's already plotted in the graph that we have. So we're just looking at, let's say I want to know how much he's going to work for 4.5 hours. So that's me interpolating around $300, 4.5 hours. All right. Now, let's say that we are actually looking at how much it would cost me if a plumber came to my house and worked for 10 hours. So what I'm basically doing is I'm going to put 10 where x is. So that's the equation. So we're doing 60 times 10 plus 40, which is the call out fee. So that's 600 plus 40. So that is a whopping $640 for 10 hours of work. Now, I don't even want to begin to think about what would cost me $640 for 10 hours of work. But again, we're just extrapolating, which is an important thing for us to remember as well when it comes to linear models. So that is linear models. Hopefully that kind of gave you some clarification about any things that you were kind of struggling with. If you want a little bit more detail or if you have other questions, make sure to check out our notes and there's more information on there as well. Thank you for watching. My name's Bhakti and I'm part of the team here at Elucidate Education. We're a non-profit organization that helps young people succeed at school. If you want to find out more about our course content, then click here. And if you want to find out more about us or help support us, then click here.